Welcome to this recording of a lecture for section 3.3 from our calculus book. We're going to go through the definition of derivative, talking about the vocabulary of calculus, and do some problems in the in-between time. The derivative of a function is defined using this expression. It says if you have some function f who's a function of x, then the derivative is called f prime, and it can be found by taking the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, that's great. It's great mathematical notation. It's very, very tight. It says exactly what we mean to say. But does it give you a lot of insight about what's going on here? Probably not. So let's see if we can draw a picture of what's going on. So let's say I have some function. There we go. In fact, let's make the function a black line, so it stands out against the axis. Let's say that there is some location on this function where there's x, and then this location right here is the coordinate x comma f of x. Now, let's say we move some distance h from x, and now we're at x plus h, making this point right here x plus h for the x coordinate and f of x plus h for the y coordinate. Now let's say we then say, what is the slope that goes through those 2 points? Well, first of all, that line is called a secant line. And if x is large, this secant line is the average rate of change for that function as x goes, or as we go from x to x plus h, right? But we don't want h to be large. What we're saying is, well, what happens when h gets closer and closer to 0? What happens is that if h gets closer to 0, then these 2 points get closer together. And ultimately, h is so small, it's like the 2 points are right on top of each other. When we get to that point, this line is no longer a secant line. It's referred to as a tangent line. And if I wanted to know the slope of that line, whether it be the blue line or one of the green lines, I would take the difference in the two y values, f of x plus h minus f of x. Think of that as y2 minus y1. And I would divide it by x2 minus x1. This being kind of like the x2, this kind of being like the x1. And if we clean that up a little bit, these two x's cancel. And if we said, what happens when we pull those 2 points together? What happens when h gets really, really small, or really, really close to 0, as I should say, right? And that's what we mean by this definition of a derivative. We mean what happens, or can we find an expression that represents the slope of the tangent line for some function x, for some function f. That's one way of demonstrating it. Let's say, take a look at another way. I happen to have a little calculator demonstration that we can run as well. Okay, in this demonstration, we have a function. The function happens to be the x squared function. We do have a value of h. Currently, the h is -3. It's close to 0. It's not 0, but it's close to 0. And I have down here a calculation of the slope. With h being -3, and this point, fixed point right here at 1, that's going to be like our x. the slope is 1. And what I can do is I can say, well, what happens when h gets closer to 0? Well, now the slope is 0. Does that look like a good representation of the slope, the tangent line slope, coming through that fixed point? No. Well, maybe I can make h a little bit closer to 0. Now there's -1. Well, that's looking closer. Okay, how about I get even closer? Well, I get undefined there when h is 0. Oh, yeah, because I'm dividing by h in that expression. When you divide by 0, you get something that's undefined. And then, of course, h can then get bigger than 0, and you can see that those slope values are changing. The one that's undefined, we don't know what that is, but the two numbers on either side of it, 3 on that side and 1 on the other side, they are reasonable guesses at the tangent line slope. But perhaps we can do better. Perhaps we can make it so I can make h get bigger by numbers that are even smaller. So now instead of getting bigger by 1s, they can get bigger by 1/10. And look at that. I can get those points really close together. H now is -0.1, and we get a slope of 1.9. And if I go one more step, up, h is 0, I'm divided by 0, I get undefined. Now I'm at 0.1, and I'm seeing 2.1. Wait, so my guesses now, when I get those 2 points reasonably close, are 2.1 and 1.9. Now, the answer is probably somewhere between there, but currently, when h is 0, we get undefined, we don't get our information out. Well, what if we move h in such a way that we're moving by 1/100th? Look at how close those 2 points are getting together. Now they're only 1/100th away from each other, and the slope between those two very, very tightly spaced points is just is 1.99, really close to 2. And at 0, still undefined, and just beyond there, 2.01. So you might be thinking, hey, I think as h gets closer and closer to 0, it looks like the slope is somewhere around 2. And you would be right. But let's see if we can do something in a little bit more rigorous fashion, right? Let's say that instead of just using the calculator and pulling those 2 points closer and closer together, we actually find the derivative of f of x is equal to x squared. Now, before we do that, take a little thing on the word derivative. Now, the word derivative, you might have heard it used as a derogatory term. Oh, that music is so derivative, meaning that artists use somebody else's work or somebody else's style and then just modified it slightly for their recording. Derivative means it comes from something else. When we say we have a derivative function, we mean it comes from another function. It derives from this other function. Secondly, maybe you remember in geometry, you'd have, I don't know, you'd have some triangle, and then you would reflect that triangle over a line or axis of reflection. And this point would be A, and this point would be called A prime, because this point came from A, that point. Same idea. We're going to find, we have starting out with some function f, we're going to find a function f prime because it comes from f. Okay, quick comment about the domain, since this is a function, the domain of f prime may be smaller than the domain of f. Wherever f prime exists, and we'll have to talk about why it may or may not exist later, we say that the f has a derivative. Okay, and we say that a function that's differentiable on every single point of its domain is called a differentiable function. Well, let's go ahead and let's find the derivative of x squared, right? So we said that, again, f prime is equal to the limit as h approaches 0. Okay, I'll write down the definition one more time. F of x plus h minus f of x all over h. Now, what is f of x? we said that that was x squared. But what is f of x plus h? Well, I can ask you easier questions like what's f of 1? You would say it's 1 squared is equal to 1. Or I could say what is f of 2? And you would say, well, that's 2 squared, and that's equal to 4. But if I said, what is f of x plus h? You might say, well, what I did was I squared the thing that was the input to that function. Well, so that makes f of x plus h equal to, or f of x plus h equal to f of x plus h quantity squared. X plus h quantity squared all over h. And there's what we're going to have to calculate. Let's do a little bit of algebra. Take this up here. The limit is h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Oh, look at that. Those x squareds cancel, allowing us to go to limit as h approaches 0 of 2xh plus h squared over h. And that allows us to factor out of the numerator h, leaving 2x plus h over h. Those h's cancel. And now those h's cancel. Now that I can do that, I can see I can plug in my 0 for h, and I get 2x plus h. Sorry, 2x plus 0, because h became 0, or just 2x. So let me summarize. When f of x is equal to x squared, we can make a derivative function. We can derive from that original function a new function, and it's f prime of x is equal to 2x. Now, that means f prime of 1 is equal to 2 times 1, which is 2, which is what we saw when we did that calculator demonstration. Yeah, it looked like it was getting closer and closer to 2. The only difference between what I did with these symbols and what I did on the calculator is this one is exactly correct. The other one was an estimate, good estimate, an estimate nonetheless, right? So we have this definition. You want to memorize that definition and be able to use it for finding the value of other functions, which is something you'll do in your practice work. But this is not the only definition for the derivative function. We have this alternate definition called the A definition. All right, same idea. Let me draw a set of axes. Let me draw some function. Let me put onto that function a point, which I'm going to say is at point A. It's going to be a fixed point. Let's say there's some other variable point called x. This is the point A, comma, f of A. This is the point x, comma, f of x. And as we've done before, there is a line that runs through those 2 points. When there's different values of a and x, that's a secant line. When we pull those 2 points closer and closer, then we call it a tangent line. We're going to say a is fixed, is a fixed point, whereas x is a variable point. And what we're going to do is what happens when we change the value of a, value of x. What happens when we make x approach the value of a? Well, right now, x and a are different. But if I pull them closer, I get different lines, and each of those lines gets closer and closer to being a tangent line until they're right on top of each other. But when they're right on top of each other, well, we got to divide by 0 error again, and that would be problematic. So let's see what happens when we try this definition on some other function, like the square root function. All right? Again, I want to find the derivative of f of x when x is the square root of x. And please note that this gives us a function f prime of a. So f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. Now let's go ahead for this particular problem. Let's plop in what we know. And that is f of x is the square root of x. F of a is the square root of a. And x minus a is right there. Now, can I apply the limit right now? Can I replace every instance of x with a? If I do, I get a minus a, which is 0. Divided by 0 is a bad thing. So let's just say I'm not to the point where I can plug and chug right now. Let's go ahead and let's say the limit as x approaches a of the square root of x minus the square root of a. And let's do a little bit of algebraic sleight of hand here. Let's say we multiply this by something commonly known as the conjugate. And whatever we do to the top of the fraction, we'll need to multiply, whatever we multiply to the top fraction, we'll have to do this to the bottom of that fraction in order to maintain that fraction being equal to each other. And if we do that, we get the limit as x approaches a, x squared, square root of x times x square root of x is x, and then I get a plus square root of xa, and then a minus square root of xa, and then I get a minus a squared. Nope, not a minus a squared, just a minus a. And then the bottom, I get this x minus a square root of x plus the square root of a on the bottom. Okay, a little bit of canceling. Square root of x minus a, plus and minus, they cancel. And that leaves me, as I go back up here, the limit as x approaches a of x minus a over x minus a times square root of x plus the square root of a. Get out our cancellation pen, see that those two cancel, and now we have something that we think is useful, and that is 1 over x, square root of x plus the square root of a. Now, when we look at that, can I plug and chug now? Will I get a 0 on the bottom? I won't. When I apply the limit now, I get 1 over square root a, replacing every occurrence of x with a, plus the square root of a, or I get the square root of 2 root a. So let me summarize. If I start with the function f of x is equal to the square root of x, the derivative function that comes out of it is, the derivative where a is the input variable is 1 over 2 root a. But if I want to know what that function is as a function of x, it would be 1 over 2 root x. Great. I have now been able to find the general function for the derivative of the square root function. If I want to know the slope of a square root function somewhere on that curve, I can use this expression to find the slope of that tangent line. All right, let's continue on. We've got a lot of new vocabulary, so we want to make sure that we can speak that vocabulary, speak it to each other successfully. Just want to let you know that besides f prime of x as the derivative of the function x, well, sometimes we write our functions as y as a like x squared. When we take the derivative there, we might use the notation y prime. And that's the way we pronounce it, y prime. Right? The disadvantage of this is that, well, it's easy to write. Y prime is easy to write. Here, we know it's a derivative function because of the prime, and we know that the x tells us what the independent variable for that function is. No such luck on this one. Leibniz, one of the developers of calculus, also gives us another set of symbols, a dy, which you can think of as change in y, and dx, which we can think of as change in x. Oh, the change in y over the change of x, that sounds like a slope. Oh, that's what the derivative function gives us. Now, for some reason, when we see this, we pronounce it just dy dx. We don't say dy over dx. I don't know why we don't. Or sometimes we say that that's the derivative of y with respect to x, the derivative of a function y where x is the independent variable. Now, both of these expressions are nouns. This notation is the verb version. Hey, I'm going to take the derivative of this function. This is an action, making it a verb. I'm going to take the derivative. This is a noun. This is the derivative. Okay. So just let you know that we're going to use all of these notations throughout the year, and the College Board will too. All right. Now, why do we care? Well, it ends up being that rates of change are inherently interesting in terms of physics and chemistry and engineering. When you're driving a car, your position is changing with the time. We call that velocity. That's interesting. So we think that slopes, tangent line slopes, are just inherently interesting. Now, we've already discussed about this definition of using the limit to define the derivative, but we can also say, you know what, we can show functions in other methods. For example, we might be given the XY relationship in the form of a table or a scatter plot. And we might be asked to find some estimates of derivatives this way. We might be shown the function graphically, like we have here. And we could say, well, here's the function f. I wonder what f prime looks like. Well, what do we think the slope at point A is? Well, it says here the slope is 4. So, hey, the x value is 0. The slope is 4. 1, 2, 3, 4. Hey, I think the f prime function would have the coordinate 0, 4. Again, because the original function, when x is 0, has a slope of 4. Let's try that again. All right, looks like at slope B, or point B, we have a slope of 1. Okay, and that's when x is 1. So it looks to me like f prime might have a location 1 and a slope of 1. And I can put that in. And that's another point in the f prime function. Oh, what about at 2, at point C? Oh, it has a slope of 0. It looks like the x value is 2, but the slope is 0. So maybe at 2, I can put in a point 0. Oh, what about when x is 3 at point D? Oh, it looks like when x is 3, the slope is -1. Oh, I need to put a little thing in for -1. Looks like I'm right there. And what about E, when we're at 5? At 5, it looks like I got a slope of -1 again. So here's 4, here's 5. So maybe I'm here. And then at 6, at point F, we're back to 0. When x is 6, the slope is 0. So these are all coordinates that are in my f prime function. And if I want to get fancy, I suppose I can try to connect those dots, something like that. And that is an estimate of what we think the f prime function can look like. All right, let's go on. More definitions. A function is differentiable on a closed interval if it has a derivative of every interior point on that interval. And if its limits, these two limits here, also exist. Now, here's something we're going to sort of battle with, this idea of a right-hand limit, or right-hand derivative. So I want you to imagine that I am at some location A, and I've got some function that only exists to the left of A. Well, I can try different values for H, make that value H, and do the whole secant line thing. And H can get smaller and smaller and get closer to 0. Okay, but H could also be like close to 0 and negative, but there is no function. Whoops, making that a little bit less. There is no function over here if H was negative. So it would be very difficult to express that notation, that expression, to evaluate that expression when h is negative. So maybe we say something like, maybe we don't look at the negative values of h. Oh, let's only look at h as it approaches 0 from the positive side. And we call that a right-hand derivative. I only look at those secant lines getting closer and closer, but only while h is positive. So I never venture in this area where the function's not defined. Okay, I might put over here a point B, and this is where the function again stops. I might say something like, all right, what if I want to find a left-hand derivative? What do I find the derivative of that point? Well, in this case, here's a point. Now, what's the relationship between B and H here? Well, H is smaller than B. Or sorry, the distance H is going lower than B. So that means for these points here, I'm drawing these secant lines, so H is negative. If I want the left-hand derivative, I'm just saying, let's limit ourselves to the values of H that get closer and closer to 0, but are negative. All right? Now, one little sort of reminder of your pre-calculus days. We only say that the limit as x approaches a of f of x exists if, when x approaches a from the positive side, is the same as the limit as x approaches a from the negative side. Okay? We're going to say the same thing here. We're going to say that the limit as x approaches, or h approaches 0 exists only if the right-hand side and the left-hand side are equivalent. So let's see this play out. For example, we want to know what goes on at the very interesting point where this piecewise function, where it's x is equal to y is equal to negative x until I get to 0, and y is equal to x after 0. I'm interested in what's going on right there. Right? So I might say for the left-hand derivative, that's the one where I'm taking 2 points, a fixed point and this movable point, and I keep on moving this point closer and closer. Or I might say the limit, oops, try that again, green thin. The limit as h approaches 0, but from the negative side, of f of x plus h minus f of x all over h. Or in this case, the limit as h approaches 0 from the negative side. My function, when h is 0, okay, by the way, I'm going to call this left-hand derivative at x equals 0. When h is close to 0 but negative, the values inside this, the input of that function are negative, which means I must use that part of the piecewise definition, negative x minus f of x, would be f of 0, because I want to know what's going on at 0. So actually, I'm going to rewrite this. X 0 plus h, f of 0, and that's 0. And I'm all over h, and this is no longer negative x. This is negative h. So if I get that right, f of h, when h is less than 0, is negative h, because the expression in here is slightly negative, and when I'm negative, I have to use that definition. Okay, let's clean that up. The limit as h approaches 0 from the negative side, ends up being negative h over h, which is -1. Now there's no h's to plug in. I can plug and chug. We get -1. The left-hand derivative is -1. Let's just take a quick look and see if that makes sense. For every single point that I go on here and I compare those moving points and its slope going into that fixed points, yeah, those all look like slopes that are -1. Let's do that again, but now let's do the right-hand derivative at x equals 0. That'd be the limit when h is approaching 0, but from the positive side of f of 0 plus h minus f of 0 all over h, or limit as h approaches 0 from the positive side of f of h minus 0 over h. Now, f of h, when h is slightly positive, that's using this definition, which means it ends up being the limit as h approaches 0 from the positive side of h over h, which is equal to 1. Hey, I got a left-hand derivative of 1. I've got a right-hand derivative of 1. These two derivatives don't agree. These two limits don't agree. And as we said from the other things having to do with limits, when two limits don't agree, we say the limit doesn't exist. When the limit represents a derivative, that means the derivative doesn't exist, at least not at 0. So we have our first indication of a function whose derivative has a domain that's smaller than the domain of the original function. All right. Let's try this out one more time, just to make sure we got it. Okay, again, here we have a function, and we're interested in what's going on at x equals 1. Let's talk about the left-hand derivative. Imagine these 2 points. What do you think the slope looks like between those 2 points? I think the left-hand derivative, as these 2 points get closer and closer, every single slope between those 2 points ends up being -1. Now, what if this fixed point is being approached from the positive side? This looks like the point, by the way, 1 comma -1. This looks like the point 2, 2. Slope between those two. 2 minus a -1 over 2 minus 1. That looks like a slope of 3 over 1 up 3. Oops, sorry, didn't do that. Over 1 up 3. Yeah, that looks about right. Looks like the slope is 3. Do you think that slope is changing? Is that point's getting closer and closer to 0? Doesn't look like that to me. Looks to me like the right-hand derivative is equal to 3. Hey, because the left-hand derivative does not equal to the right-hand derivative, our conclusion is, therefore, derivative of f doesn't exist at least x equals 1. All right, so there's our a quick set of lecture notes for this. Hope it was useful.